Okay, so this is my system. This is just a simple GUI system that will only consist of four components, which will be a button, a text box, text label, and drop down menu. It will not have a layout manager, and absolute positioning will be used. Positioning and sizing will be based off of pixels. So this is mostly self-contained. It has very simple features, allowing client programmers to just like place text boxes, text labels, buttons, and drop-down menus to the screen. We assume users are programmers with experience within graphics and general programming in C++. So you need to have like knowledge of linear algebra, 3D spaces, programming, C++ best practices, and the rest. The operating environment is considered to be a computer. This is not meant to be running on embedded systems, and operating systems allowed are Linux, Apple, and Windows. So for design and implementation constraints, we had to use version 3.3 of OpenGL, considering that the core version of 3.3 is the only version supported on Apple. For functional requirements, we assume that the client programmer passes function calls as form as input, and that is transported to output as rendered components on the screen. Every GUI component must be rendered correctly. Memory allocation must work properly, and the gap buffer must also work for text editing properly. Upon errors, the attempted GUI component will not be drawn, and a message will be printed to the programmer detailing the issue. Non-functional requirements: the system must be performant. It must be reliable. It must be testable. Yeah. And for external interfaces, we need some sort of C++ programming environment, such as CLine or NeoVim. If you want to configure your own environment, this is supposed to be used with OpenGL, GLAD, and GFLW as external libraries. And so yeah. And the system features is that it has a button, a drop-down menu, a text box, and a label. And it essentially enables you to just call these, configure their data, and have the renderer draw that to the screen. And that's really it. For software design, it's we just want to, in this document, we just want to outline how the components themselves are designed. So the system architecture is fairly simple. You have these models, which are the button, text label, text box, and drop down menu, which are just full of data. This data is then fed into the renderer, and the renderer takes that and it transforms that into output onto the screen. And user interaction can then modify these outputted renderers by like changing data within the data models. This architecture design most closely fits the model view controller, and models being the GUI components themselves, the view being the renderer, and the controller being user interaction messing with the data within the models. So for each component, we'll go over the design. The renderer is simply takes data from each model. The models are within an associated list, and that's fed into the renderer, which will draw each of these GUI components, and that shows up as something on the screen. The button, text label, text box, and drop down menu are all just data structs, essentially that hold data such as like width, height, position, text, character limit, whatever associated data they may hold. The text box and button have a special attributes. The button has a callback function, which will be performed upon the button being clicked, and the text box has a gap buffer, which is used for editing text. The interface design is fairly simple. GFLW, GLAD, OpenGL all enable rendering of the library without having to interface directly with the OS itself. They just make it much easier for graphics to work. Data design, the data structures usually be arrays, buffers, a gap buffer, an arena, and vectors. Vectors and arrays, of course, will be used to store associated data, like arrays can be used to store characters, vectors, GUI components, and buffers can be used to collect things like keyboard event presses and so on to be relayed into the controller for modifying GUI components, and the gap buffer is simply a data structure used for editing text. Data flow is again fairly simple. I explained it. Model data is sent to the renderer, which will then transform that into viewable output on screen. and then you can use the user interaction component to mess with how that is portrayed. Hardware limitations, it's really only meant to be used on computers. Again, this is meant for users to like quickly ideate through things. Yeah. Performance constraints, no real ones. Essentially, we don't want FPS to fall below 60 because this is not a very intensive application. Development limitations, the only real development limitation was to limit the amount of GUI components and not to use a layout manager, only absolute positioning. For safety, we wanted to memory safety, so we created a memory data structure to essentially manage memory for us, so there are no memory leaks. Major design decision was really based around the fact that we wanted this to be a quick prototyping, ideation, software sort of thing. So that was our major component consideration, our design consideration. So this is supposed to be a simple, lightweight, extensible library, essentially. So if you want to add your own GUI components, you can do that. The purpose of this document is to list out what we're testing and what about the components we're testing. So for the render module, we're going to just simply test whether everything is correctly rendering. For the gap buffer, we need to test functionality such as movement of the gap, dynamic resizing, and resizing the gap when it's full. Memory allocation deals with alignment of the data, correct valid pointers being returned, and dealing with the memory buffering being full and ensuring data is not overwritten. Over interaction, we're just ensuring that we're getting correct, we're sending the correct data to the memory, to the data models to be modified, and ensuring that the correct characters are being captured from the keyboard, and we capture mouse input as well. We're not testing the data models, they are simply models for data. They're literally structs, there's no purpose in testing them. So we use unit integration system testing, unit testing for the gap buffer and the memory allocation scheme. Integration system testing is mostly for the overall system to see how different components are interacting with each other and if things are running properly. A black box approach will be used for the overall system to see if from a test application that we wrote, whether it's being properly transformed into pixels on the screen. And a gray box approach used for testing the memory allocator and the gap buffer. So some library memory leaks, so that can be a risk. Essentially, test cases that successfully pass are considered a pass. Any that rises to fail. Memory bugs are fails, and if GUI components are not properly drawn, that is a fail too. Suspension is when a test fails and we resume upon the test being fixed. So correct rendering of every component is a test case, and we're just using the renderer to render whatever. And the gap buffer unit test just tests these various things about the gap buffer, all this stuff. And for the memory allocator, we again just test these certain things about the memory buffer. Essentially, we're just testing to make sure functionality is ensured. Test procedures. The first step, we're just properly setting up the environment for the testing, and then we run the test, really. Execution, we just run the test application or the test, and then that's all we do. And teardown, well, the test will just automatically clean themselves up once done, and that's really it. For the test summary, test environment will be a fairly simple laptop, and we'll just use it to build the software and run the software, and that'll really be it. Okay, for the demo, see here, you can type in the text box. This is our text label, and you can see you can select things. You can click on the button. So yeah, pretty cool. This is just the thing. See the text box, this, and of course the text label up here. That's it.